welcome to another stream. I don't know what time zone you're joining from. Here it's a little past 9 p.m. And, so a little bit late, but my schedule is often, I don't know, I like to be able to work on stuff whenever I feel inspired, and I've been feeling inspired on this right now. Also, this is the first time I'm streaming something that's kind of technically part of my kind of day job, what I'm doing for that, but not necessarily something I'm always doing during the day. I might actually have an opportunity to start this with a quick visit with my cat, because he seems to want some attention right now. Oh, that's not actually my cat, that's just a picture of him. And that's just a box. Hey, Tuco. How are you doing tonight? Got a bit of an autofocus issue with this camera. Alright, hey Tuco. So, I think maybe this is a good opportunity while I satisfy my cat's lust for bolts just a bit to give a tiny bit of background on what this even is that I'm about to demonstrate / work on. So maybe some of you have seen a video that I put out before / a POC or GTFO article I did. A series of work that I was trying to document. Hey Tuco, where did that bolt go? There it is. And the gist of it was a way of getting the firmware out of devices that you don't have otherwise access to. So there's no firmware update mechanism, or it's encrypted in a way that you can't get access to. The JTAG debug port's locked. All the usual things you wouldn't have access to the firmware. But I was demonstrating how there's not that much of a difference electrically between a device returning its USB descriptors, kind of telling the computer what driver to load, versus if it's actually handing back an image of its firmware over USB. So you can introduce an electrical glitch at just the right time and cause the USB descriptors to end up reading back, with an incorrect length or an incorrect pointer. And so that's how I was able to get a firmware dump from these the Wacom tablet that I was working on before. So this is about trying a similar technique, but with a device that, instead of being accessible over USB, is mostly accessible over Ethernet. And I'm hoping I can do something similar where, so this Ethernet attached microcontroller is kind of a common, or at least it seems like it has the potential to be a pretty common sort of, wired Internet of Things device. It's this, so this one happens to be a chip made by TI that has this ARM core plus an Ethernet, PHY, and MAC. So all of the hardware you need basically to just plug this thing into the transformer and like an external 3.3 volt power supply and an Ethernet switch, and now you have a thing that you can connect to the internet. And so that's the kind of device I'm trying to see if I can get firmware out of right now. So actually, I'm going to go ahead and start the audio recorder, because I think I might end up using some of this explanation, at least for reference dialogue later. Oh, hey, nice to see some visitors in the chat. I wasn't sure how many people will be around for such a kind of late night stream here, but you know, I know I've seen people from all over the place, so I'm sure there are for a lot of time zones, this isn't super late. And then I also know probably a lot of you are night owls like me. Hey, Duke, where did that one go? Oh, there's also a comment in the chat, a request to hack a router. And actually, that's a pretty good request. I don't know if I'm going to get to it necessarily immediately because I already have so many other things going on, but I have to ask. I'm curious what you mean by that, because there are a lot of different ways you could hack a router, and even some, you know, from like, I can imagine trying to find, you know, like, there's the kind of like, flashy kinds of things, like finding new vulnerabilities in routers and finding like, you know, oh, here's a backdoor or here's a remote code execution or something. But then, you know, that's actually not how most routers end up getting compromised. You know, most of the problems we've been seeing right now are just people not setting their stuff up very well. And then, but then you have, oh, hey, Tuco. Then you have stuff that I think from some perspectives might seem like hacking a router, just like installing OpenWRT on it. That's actually pretty useful. And so yeah, I'm kind of curious what you wanted. Good cat, Tuco. He's been really into this. He really wants to continue this. So I was in the process of giving a little bit of background on this particular glitching project. So with the USB glitching that I already have a video out about, with that, the device included some code that's part of the standard USB device framework, where you can ask it for a descriptor, and it looks up that descriptor in a table, and it returns a binary blob that's compiled into the firmware that then tells the operating system some information about what driver or what combination of drivers to load for that device. And so, you know, some devices do something complicated with that descriptor command, but generally, especially for simpler devices, like the kind of 8-bit device that I was working on at the time, it's pretty common just to have like a pre-compiled table with the raw data that you would be sending back, and then to have some other tables that list pointers into that and lengths, and then you basically just have a general purpose descriptor parsing or descriptor processing command that's all table driven. And so in this case, the glitch was corrupting some of the calculations, and it didn't actually need to even affect the location that it was reading from. It just affected the length bound and caused the read to just continue past the end of what would normally be the end of the descriptor, and then just keep returning firmware. So the thing that I'm trying to do right now is a little bit like that. It's still basically, I mean, it's the same thing basically, where I'm trying to affect some data structures in memory that return, or that store either a length or a pointer to some data in order to get it to return different data. In this case, it's actually file systems, or files that would be returned from an HTTP server. But this is a really tiny embedded HTTP server, so this is even smaller than what you would find on like a stripped down Linux on a Raspberry Pi. It's more like what you would find in like the Arduino, you know, networking stack or something like that. It's if you get the example code for this board, which I have a hunch a lot of the devices just copy and paste the majority of, they actually have examples for a couple of different TCP/IP stacks, and it turns out that you can tell what stack a device is using because it'll include the like kind of open source license details for that stack. So the device I've been looking into is this industrial logic controller, and as far as I can tell, like so far its behavior, the behavior of that device looks really similar to one of the examples that I'm finding in the Texas Instruments development kit for this processor. So I've got one of those development kits, and just in order to remove some of the variables and take away some of the other stuff that's going on, I've got this board set up that is configured pretty much the same as this real-world device that we've been looking at. Such a good cat. But I've been trying to kind of simplify it as much as possible, and one of the important simplifications has been to kind of narrow down when the interesting code is. With USB, my approach was to try to have really careful control over the timing on just as much of it as possible, and then just exhaustively search the space. And that was really fast once I got rid of all the sources of kind of extra non-determinism. And then it could just kind of stay synchronized from pretty early boot throughout the whole experiment. With this Ethernet, I'm taking a slightly different approach, because even some of the earliest tests I did, where I was just looking at the timing of like ping and HTTP responses to figure out if anything observable was correlated with the timing of an HTTP request, then I was noticing that there was just a ton of jitter. Like it was as if there was a main loop that was running with, say, a 10 millisecond period and servicing outstanding requests. So if that was the case, then sending out the packets with a known timing wouldn't really help. And I would want to really have a way of synchronizing to something that I can measure that's kind of close to the HTTP request. So with this real-world device, I think I found a way to get it to give me an I/O and a file readback in the same HTTP request. And that's way outside the scope of this. I mean, unless we want to get into a big rabbit hole, but that's quite a diversion from this particular thing. For this simpler test, instead of having to use that weird HTTP trick that I'm using to get it to send back or do the GPIO and the file read at the same time, since this is just example code, I just modified the example code to insert a GPIO trigger right before some piece of code that I think might be really interesting to glitch, which in this case is looking up a file from this file system that's really just a data structure that's baked into the firmware. And then, hey Tuco, is that one stuck? So after it looks up this file that's in its sort of ROM file system baked into the firmware, is that one too stuck, Tuco? I think there's another bolt over here somewhere, so he won't be disappointed. I think that one went behind the refrigerator or something. He's very persistent, but he doesn't have infinitely long arms. That would be weird. So anyway, I've got so with this system, my approach has been more to synchronize very close to the request. And I'm still getting some noise and stuff, but it's been helped. Oh man, there are a bunch of things that made this more complicated. So besides the kind of having to give up on the synchronization a little bit with Ethernet, the processor is also just much faster. So Tuco, are you finding something in my pile of junk? Still need to reorganize so many things here. Anyway, so also the processor was just kind of electrically a little more challenging to glitch. So with the USB, with a little 8-bit USB microcontroller, the CPU speed was pretty low. I think it was 32 megahertz or 24 megahertz, something like that. Oh, maybe 12, but yeah, something in that neighborhood, something that's pretty easy to deal with. Good job, Tuco. So with that frequency, it was pretty easy to have the chip whisperer hardware generate the clock signal directly, and oh, that's what it was, 12 megahertz external clock, because that's really convenient for USB. USB likes 12 megahertz. Anyway, in this case, the external clock is actually set by what's convenient for Ethernet, which is 25 megahertz. And so it'll multiply and divide that in various ways depending on whether you're doing 10 base T or 100 base T. But then the actual processor core is much faster too. We're talking about like an ARM Cortex M4 with floating point, and it's usually clocked at 120 megahertz. And so the way that works is via a phase-locked loop that takes that 25 megahertz and then multiplies it and divides it again and ends up with this. And so the chip has these programmable clock dividers that you can set in all sorts of different ways, but they probably just, again, copied the example code from TI, so I can kind of guess how the PLL is set up. And so originally with this glitching setup, I wasn't really having a whole lot of luck in getting reproducible synchronized traces or putting in glitches that had much of an effect other than either no effect or crashing. And so some of the most recent changes to the setup to accommodate or to try to get past those problems, I've been able to just underclock the entire system. So, hey Tuke, did you lose that? Or did I give you a hard one? So I've kind of taken a page from the playbook I was using with the Nintendo DS ages ago. And with that system, the whole thing was clocked a little too fast for the tools that I had at the time, and I wanted to actually interact with its memory bus, which is pretty fast. I think normally it would have been, probably a little over 100 megahertz in that neighborhood. But since I can control the oscillator just by replacing the crystal with my own clock source, I can underclock it. And there's usually a limit to how far you can underclock a system. Oh, did you find it, Tuco? Good job, boy. Good job. Got some dust. So the underclocking limits usually tend to be the analog components in the system. The PLLs and capacitive or inductive coupling, where if something is just a static signal, it won't mean anything. Yeah, in this case, I was able to underclock it by about a factor of 4. So that 25 megahertz clock, I can actually give it a 6 1/4 megahertz clock, and accordingly, everything is a quarter the speed. And then to communicate with it, I have another Ethernet device which I feed with a matching slowed down clock, so that they can kind of agree on the time base. Oh, I was trying to check the chat and I forgot how the computer worked. There we go. Oh, there's a clarification in the comments about the hacking the router post, and that's actually a good question. It's the question was actually more along the lines of what I was doing with Coaster Melt and kind of getting into this kind of unknown black boxy kind of system. There we go, Tuco. And getting out its firmware, that kind of thing. And I could do that kind of thing with a router, but most routers are actually really, really easy to do that to. Like, you can just look up the model number of the router and download the firmware, and often it's just as easy as untarring it. There's actually also a tool that you can use to automatically unpack a lot of firmware images called binwalk. It's like a Python tool. And so most appliance kind of devices that hang out on your network and have a web interface and all that, a lot of those just run Linux. And in that case, typically you can just get a file system image out of them if they're updatable somehow. You can download one of the updates that are meant for it and then extract its file system update. So usually it doesn't require going to quite the lengths that I had to with that system on a chip, since routers tend to be a little bit more general, close to general purpose computers than other systems. All right, I think CatCam has served its purpose. Let's go back to this. All right, got our tea, got our crazy setup on the desk. Oh, I'm also appreciating this new, I got this new machine in the mail from a friend to act as a much better kind of YouTube control panel than the Chromebook. I'm not quite used to how it stands yet, but it's a much nicer machine. Alright, I think I might need to maneuver the camera a little bit to get a better view of everything that's going on. Alright. Well, let's start with the device under test over here. See if I can lock this down. Okay, and stop wobbling. So that is the microcontroller that we are trying to, as an experiment, extract the firmware from. In this case, it has known firmware. It's just something that I compiled on my laptop. But you can see a lot of the same modifications that I demoed in the other video. Let me take this probe off. I don't need it right now. So in this particular board, well, I'm not actually sure how much good it does separating. So I was going to talk about this resistor. Let me point it out. So on this particular board, actually, I have a second one of these boards because I got a spare, so that would make a good demo, so I don't have to handle this one as much. Oh, I thought I had that up. Ah, here we go. I think I found a tiny bug in the YouTube chat client. Oh yeah, so... Oh, can we get that here? So that's the kit here. It's the Texas Instruments. I think this is kind of one of their main products for if you want to make an Internet of Things device and stick it on a network. They want to sell you this chip. And they have this nice marketing name, the TIVA Series C, but I had only seen it as the TM4C 129. So I had not known that there was a friendlier name for it. And there's the board. And this is sealed. Oh, yeah, I think this particular YouTube bug was like I tried to have another tab open with the chat popped out like in anticipation of wanting it to be easy to access, but then like that popped out chat didn't automatically reconnect, so the chat was like homed over in the like dashboard tab, and then I checked, you know, so I was using it there, then I switched to this tab to see, oh, is this alive, and it wasn't. Then I switched back to the main thing, and it looks like in the process of checking to see whether it was alive and thinking that it had failed, it had actually become alive. So then that's what I wanted, just not what I expected. So anyway, I think is that as close as I can focus? No, great. Huh. I guess I need to move the camera very slightly farther back. Much better. All right. So this board is one of those like amazingly cheap TI dev boards where it's just barely more expensive than the processor itself would be in small quantities. So they're really trying to push this on engineers, which is nice when you want to use it as an experimenting platform. It's got all these big 0.1 headers. This thing in the dotted line is like their onboard debug interface, which is actually another chip in the same family acting as a USB to JTAG bridge. And so I used that with the TI official software to install their example. And you know, on my own project, normally I would want to use an open source toolchain for something like this, but in this case, since I'm trying to replicate the most common environment out there, and in particular the environment that I'm guessing that this particular product I'm working on might be using, this is most likely just going to be running whatever is kind of easy according to the TI documentation or whatever the downloads have available. So in this case, yeah, 120 megahertz, LWIP, TCP/IP core, and TI's own compiler. And this is the pulse transformer. This is actually one of the things that I might want to take out on this stream, since I can get this underclocked by a useful amount, but I might be able to underclock it even more without the transformer, and it might increase reliability even at the current clock rate. Because I think I'm getting the occasional Ethernet glitch because of the kind of really disgusting waveforms that are making it through this pulse transformer at the lower speed. The other thing that's kind of helpful about this in this circumstance is they actually have a separate 3.3 volt plane for the microcontroller that is disconnectable from the main 3 volt plane using this jumper. So that's perfect for if you want like a current measuring shunt. You can just disconnect that and put a resistor across it. So that's what I did on the other board. I'm not clear how much the resistor is actually helping, because part of what's weird about glitching this board is, unlike the other one, this chip has a built-in low dropout regulator, since its core voltage is, I think, 1.2 volts. And so it has 3.3 volt inputs, and a lot of the logic on the chip does need 3.3 volts. The clock synthesis PLLs have their own separate 3.3 volt rail. Of course, the analog inputs and the Ethernet transceiver needs a lot of 3.3 volts to transmit. So a lot's going on there, but then there's a separate, so there are actually 2 pins on here that are just for that 1.2 volt core voltage. And so that's kind of handy, and it's kind of annoying. And it's kind of nice having the CPU core separate-ish from a lot of those big loads, but it still doesn't really isolate it from Ethernet. Like, I still see tons and tons of noise measuring the tiny fluctuations in the 1.2 volt rail because of the 3.3 volt swinging around all over the place trying to transmit. And I mean, I'm sure part of that is because I put that shunt resistor in, so I'm doing the same. I'm trying to some extent the technique from before, where I try to really stabilize the power coming in, on sort of this side of the 3.3 volt shunt. But then there's a resistor which is allowed to drop a little bit of voltage that depends on the current, so I can measure the current. And then on this side, it's just, I think that's probably doing more harm than good in this setup, because the actual measurement I'm doing is on the other side of the LDO regulator. And it's really just a question of, when I'm actually causing the glitch, I need to, I need to create enough of a power dip that the LDO can't just like keep shoveling in more power and kind of negate the effect. And I think that might be to some extent what's happening. I've been getting some okay glitches, at least on the oscilloscope, with the glitching transistor on the chip whisperer light, and kind of the easiest setup. But I think another thing that I might try to do on the stream is to put a MOSFET just as close as I can to that 1.2 volt rail, so that I can kind of create a faster falling edge that might be better at causing faults in the chip. Because the thing I'm getting right now is just the glitches aren't really doing much. Like, they make the power bounce all over the place, but the chip just keeps on going, and I'm not actually seeing registers or kind of control, you know. What this would do is it would cause a control flow difference, either because the control flow is being directly manipulated or because some data is being manipulated. But I would see some change in the kind of power trace that shows me what the chip is doing. So that's what I would expect. All right. Yeah, there's another clarification in chat, whether there's an LDO for the vCore, whether that's internal, and yeah, it is internal to the processor, and there isn't really a way to disable it. So, you know, especially if you don't have access to the firmware. Like, I think if you're writing firmware, there are, you know, like you can definitely adjust the clock and turn off the PLL and do stuff like that from firmware. And I think there's a way to adjust the LDO in firmware, but on a chip that's locked out with no JTAG access, then that wouldn't really be an option. And I mean, there isn't really a way to turn off the LDO. I mean, I've thought about whether it would be more useful to, instead of using a MOSFET, to just momentarily short the LDO to ground, like what I'm doing right now. Like whether that's better or whether it's better to just kind of try to overpower the LDO uniformly. Like the other idea I have is instead of kind of leaving the LDO operating normally and then glitching it and then letting it go, and then when you let it go, it kind of bounces around, settling down again. Instead, have a just like a really high power op amp just drive vCore directly, and then you can kind of do whatever voltage step waves you want to try to induce a glitch. I think that might be better because that would have less of a uncontrolled effect once you release the glitching transistor, like what I'm seeing right now. But I'm going to try this a little bit first because electrically it's way simpler and doesn't require an expensive op amp. Tuco, do you want to fetch? Tuco, where's the bolt? That's a piece of lint. That's not a bolt. No, the bolts are over there. Oh, yeah, and that's another good question about the capacitor for the LDO. And it does have an external capacitor, which I've been playing with, because that's another delicate balance, because for the glitching, you really don't like the capacitance because that makes it hard to get that fast glitching edge, because, you know, the MOSFET has to fight against that capacitor full of energy. But without enough capacitance, the LDO oscillates, and then the chip is just no good. It just doesn't run at all, or it resets, you know, very rapidly. So yeah, I think on the other board I've got. Well, I originally had, I think, 1 microfarad on there, and I think the data sheet, like I think it's nominally like 4 microfarads and minimum 2 microfarads, and I've been having okay luck with 1 microfarad. But I've just recently been trying to kind of cut down on some of the lower frequency noise in the traces now that I can see the CPU a little more clearly, and you know, that's something that changed after underclocking it specifically. So after underclocking it, I've been thinking, and I added a, actually I can point that out. I shouldn't touch it with the tweezers because it's on right now, but, right. I keep, I'm expecting this to be like bottom heavy like a laptop, but it's a Surface, so it's all top heavy. So, hey Tuco. Alright, a non-conductive pointing device, like a mechanical pencil that's not poked out. Okay, so yeah, that's the vCore LDO capacitor that I've been tweaking. There were actually 2 capacitor spots. I think it was that and something over here. So because I took that one off, I just ended up stacking the second 1 microfarad capacitor over there to make 2 microfarads. And so yeah, there's the like 1 ohm resistor I put in as a shunt, which may or may not be doing any good. And then I kind of beefed up the capacitance on the input side of the 3v3 rail just to try to cut down on the lower frequency noise I'm seeing in the traces. And then the other major mod here is the external clock. So I did the usual thing and desoldered the crystal, and I'm using a series resistor. I think that's 47 ohms on the positive. So between the 3.3 clock signal here and the clock input where the crystal would normally have one of its pins, I've got like a 47 ohm resistor just to cut down on some of the ringing. And then it's also important to keep the ground loop area low, so especially for the clocks, because otherwise you'll just get clock interference everywhere. So that's why I've got these like twisted wires for the clock. This is just so that like if your ground and the clock wire are far apart, then like everything in that area is just like a transmitter at your clock frequency, and you don't want that. To go. Do you want a fetch break? All right, let me throw this bolt and catch up on chat and drink my tea for just a second. Oh, that's a good idea. A suggestion from the chat to use another FET to disconnect the LDO capacitor during the glitch. Yeah, that's probably what I'll do next if this seems to not be really good. Oh yeah, and as for tools, I haven't really gotten to a total tour of this setup yet. Where'd you go? So there's the device under test, and the glitching device. Ooh, that didn't sound good. There we go. The glitching device is my chip whisperer light over here. And I'm using that as a clock generator and a measurement device and a glitch generator. And right now it's MOSFET, right there, is generating the glitch by pulling the vCore low through this coax. So it's not optimal. Like, it worked for the lower speed USB micro, but like I think it would be much better if the MOSFET was on the other end of the cable. And then the other coax is the onboard A to D converter, which is now thankfully synchronized. So the way I'm achieving that is I want the A to D to be synchronized pretty closely with at least the same frequency and at least phase locked with the actual core clock on the microcontroller. And again, the trouble is the clock that I want isn't external. The microcontroller normally has that 25 megahertz external clock, and the need to go. You really want that bolt, don't you? 25 megahertz external clock, and then it bumps that up to 120 for its internal operations. So really that's what I want, but I also don't really want to have to deal with a 120 megahertz clock if I don't have to, because that's a lot less convenient than the slower clocks, and it also just exceeds what my tools here can handle. I've got a 100 megahertz scope, and the ADC on here can handle a little over 100 megahertz, but not much. And ideally, you want the A to D running at a multiple of your processor clock. So, the rate that I was using before was ×4, which is not bad. But with this, the highest I could get while trying to use the chip whisperer to clock the target directly was like 0.8 times, and it was like not even an integer number because the 120 to 25 megahertz ratio is not integer. So my solution to that was, so instead I have the chip whisperer generating. Well, all of this only works because I can underclock the whole setup, first of all. Otherwise, I would need a faster capture device, I think, to do the same thing that I'm doing right now. But I'm underclocking everything about 4x. So, so instead of a 120 megahertz internal clock, I'm shooting for a 30 megahertz internal clock. So I have the chip whisperer generating the chip whisperer. I have that generating something which is its own approximation of the 30 megahertz internal clock. So that'll be a reference which should match the clock that we eventually end up getting inside the processor, even though we can't interact with that clock directly. Let's see if we can get a scope. Oh, Tuco, you really want to play, huh? Well, okay, maybe I need to take a longer fetch break and refresh my tea and answer questions, because I know I'm kind of going into some weird territory here. So let's do that. So let's do question and answer and tea and bolt break. Let's do it. Yeah, let's do it. Here's a bolt. Let's change channel to cat channel. Cat channel. Hey, Tuco. Cat channel. All right, first question I've seen on the chat, can the chip whisperer change the clocks on the fly? And actually, it kind of has a cool system for doing that. And there are kind of multiple levels of that. There's, I think a lot of PLL designs, so it uses the PLLs on an FPGA. Specifically, I think it's a Spartan 6 Xilinx FPGA. And so a lot of those parameters are runtime configurable. So it takes advantage of that, and you can just set them in Python whenever you want. It also has some parameters that you don't need to change as often. I think it's the fine tuning for glitch pulses, but normally you would have to recompile the FPGA bitstream to change some of those into different ranges. So they actually are really clever, and Colin, he's really clever, and he uses FPGA partial reconfiguration to include different bits of FPGA bitstream that set up the PLL for different frequency ranges, or different glitch offset ranges. Good job, Tuco. Oh, that's great. There's a comment in the chat that a friend's cat is being mesmerized by Tuco as well. And that's always great when the cats can keep each other entertained even through the computer. Tuco doesn't seem to respond much to stuff on screens. He likes to rub his face on my phone because I think he knows it's something that I interact with a lot, but he doesn't really pay attention to what's on the screen. Did you decide not to like that bolt, Tuco? Okay, maybe he's done. Ha. Oh, Tuco. Yeah. All right. Back to the the other camera. All right, so in this case, yeah, let's try to get some of this on the Oscilloscope. Since, you know, pictures. It's always nice to have pictures. There's been so much talking. That's right, I already have one of these probes on the clock coming from the Chip Whisperer. Meow. Do you want to play again? That's okay. He totally wants to play. Such a fickle cat. Almost as fickle as the autofocus. This camera is decidedly not servo AF. The cat is totally servo. He's closed loop completely. I mean, I don't know, without me he might be a little bit more open loop, but he and I close each other's loops pretty well. Alright. It's not the prettiest clock. It's also a little high frequency for my scope, but there we go. Turning off long memory mode helps. Usually I'm into long memory mode, but alright, so it's bouncing around a little bit, but 30 megahertz. And let's get one of these other clocks that I'm interested in. This is the clock. Whoa. That's on a very different scale. Sweet. That's the clock that we're feeding into the microcontroller where the 25 megahertz crystal would normally go. Yeah, it's kind of hard to get those lined up because there is no integer multiple between the two. But if we get the frequencies, we should be able to see what's going on pretty clearly. There we go. That's our 30 megahertz in, 6 1/4 megahertz out. So that's what I've got. That's what I've got going on in this little FPGA that's sitting between the Chip Whisperer and the little microcontroller. Hey, Tuco. Still bolts, huh? All right. Meow. I hear you, Tuco. All right. So This is the clock we were looking at on the bottom, the 30 megahertz coming from the chip whisperer. And this is the iStick, which is a little FPGA board running an FPGA that was convenient for this purpose. It's got an onboard PLL that I can program, and other than that, it's just got like another divider past that. So the PLL takes the incoming 30 megahertz, multiplies it by 5 to give me 150 megahertz, and then I divide that by, I think, 24, and then the result is this 6.25 megahertz. And then it just outputs that from 2 pins, as well as running some LEDs, just that I can see that, you know, if the LEDs are blinking, it means the PLL has something it's outputting. Although, you can certainly get the PLL into a state where it's not really giving you a usable clock, even if it kind of thinks it is. If you're, I've experienced that some when I've been kind of trying to move the input frequency kind of outside of where the PLL was designed to operate by adjusting it in the chip whisperer. So I think we can take a quick look at the FPGA itself, because I've got the code for it on the computer here. Oh, need to mirror the screen. That's better. All right, here's the, that's the end result of the current setup. I can reload this web page. Isn't that exciting? It's kind of slow, and I think some of the packets are dropping. But if I reload it, it reloads. Yeah, and that's through a, so because I'm underclocking it, I need an Ethernet adapter that I can also underclock. And that means that my choices are pretty limited, because, like, let's say if it's an Ethernet that's built into the processor, like it is on a lot of system-on-a-chips, then you probably don't want to underclock the entire processor, because then all of your other interfaces will be kind of speaking the wrong speed. And a lot of Ethernet adapters, like if you just, like I actually cracked open all the USB Ethernet adapters I had around here just to see if any of them had separate clocks for the Ethernet part and the USB part, but they all share the same crystal. So if I were to underclock one of those, then now I wouldn't be able to talk to it over USB without an underclocked USB adapter. So I needed something that I could do to kind of act as my clock domain bridge. And so for that, I'm using this SPI attached Ethernet adapter that can speak 10 base T Ethernet. And that's called the ENC28J60. It's this this chip from Microchip that actually I've used this thing ages ago. Here it is on a little breakout board. You can't see the chip because it's on the underside of the breakout board, which is kind of a silly breakout board design. But yeah, it's under there. I might have a second breakout board around here somewhere, but I have a couple of those because of this project I did a while ago, where I wanted. Oh man, this was like very ahead of the time, like Internet of Things. Like I wasted all my enthusiasm for connecting things to the internet back when that was like super hard, and so I have like I had this old project where I think I was trying to make something for streaming audio over my LAN. And so, you know, I could buy a thing that did that, but I wanted just to have a bunch of these, and I wanted them to be cheap, so I didn't want to have to pay like $150 each. I wanted to make one that was like, you know, $10 and just have a few of them. And so I saw one route to that as having a microcontroller that was pretty fast for the time. It was a propeller with multiple cores at 80 megahertz each. And I wrote all this stuff, like all this custom stuff, you know, a custom SPI driver all the way through, you know, a lot of the TCP stack just to handle this particular situation. And so it's kind of refreshing to take that same breakout board now and use it with a normal Linux TCP IP stack on the Raspberry Pi. And that was actually remarkably easy. I was surprised at how little configuration. So I think that might have to do with the hat system that the Raspberry Pi architecture added relatively recently. but they have this whole device tree overlay thing so that you can actually just set a line in your boot config, and the kernel will load this binary blob that says, here's a bunch of hardware I have and where it's attached. And so the Raspberry Pi consortium has a bunch of those binary blobs for common things that you might want to plug into a Raspberry Pi, including this particular Ethernet adapter. And by default, it would try to talk to it over SPI at like 12 megahertz. So that itself would start to pose a problem for underclocking. But that's actually super easy to change. So in those same kernel options where you'd say, hey, I have one of these devices, you can also just say, hey, by the way, only talk to it at like 500 kilohertz, please. Be gentle. So that's what I'm doing. I've got this Raspberry Pi. So that's over here. Maybe I'll go back to the big DSLR. So there's my Raspberry Pi in the rainbow case, the Pibo. And this is actually just a plain old Raspberry Pi 1. I use that for this because it does not need to be fast. It's operating the slowest Ethernet I can imagine. And so this Ethernet is just connected to my shop network so that I can get to the Raspberry Pi. But then that's ETH0, and then that shows up as ETH1. And I can just use all the normal Ethernet tools, which is pretty awesome. But it's speaking this super slowed down version of Ethernet because, just like the microcontroller, I can just remove the clock crystal and substitute my own clock signal. So that's exactly what I've got going on here. That 6.25 megahertz clock that's being synthesized by the little FPGA here is also going off to that ENC28J60 adapter, and then they're speaking over this really short cable a dialect of Ethernet that no one else is going to understand, but these two devices can. So let's go back to what's inside this FPGA. Oh, and the reason I can reach this in the browser is I just have a TCP forwarder running on the Raspberry Pi for port 80, since that's what seemed most convenient. But if I SSH into the Pibo, actually I'm just realizing I should also start the recorder for this computer if I'm going to be demoing this, because I'll probably use some of this footage too. I'm mostly over my fear of just having like 80 gigabyte files that may or may not be useful from running this recorder. Because hard disks, like, I still try to conserve hard disk space, but they're just so inexpensive now. Oh, I should move TucoCam. He's hanging out right here next to me now. Oh, and so the ENC28J60 chip I'm using only speaks 10 base T, but in this case, that's actually really nice, since one of the things that I wanted to do to this Texas Instruments chip anyway is to force it to speak 10 base T instead of 100 base T, because it's a lot less electrically noisy while it's talking, and so it makes the power analysis easier. 100 base T is always spewing out these tokens when it isn't otherwise saying anything to kind of keep the line equalized, whereas 10 base T actually has gaps between packets. So yeah, that was actually a little bit annoying, and I actually ended up having to make sure to go in and use ETH tool on a Linux machine with a compatible Ethernet adapter to specifically set it to 10 base T full duplex. But this is another way to solve that problem. So yeah, this is my Raspberry Pi. There's the ENC28J60 attached on SPI0, the best place for an Ethernet adapter. I was kind of laughing. I don't know, a lot of you probably also watch Dave Jones's EEV blog channel. And I'm not necessarily the biggest EEV blog fan, but I do like it and I follow it a lot. And I happened to catch some of his recent shows where he was talking about building a cluster of Raspberry Pis, which sounds interesting. It's like one of those, I don't know. Maybe I'm jaded to that idea because I'm so used to like every time someone comes out with like some fast little processor, there's like a whole forum full of people who are like, let's make a cluster of these. It used to be like a Beowulf cluster on Slashdot, and then like when I was working on like that propeller Ethernet adapter and that kind of stuff, people were making clusters out of propellers, and I thought it looked like fun. I didn't think it looked useful, but I don't know. Maybe the Raspberry Pi is starting to get fast enough to where like with a like a desktop case full of Raspberry Pi 3s, that's probably actually quite a lot of power. So, but then he was talking about connecting them together using this exact thing, which is actually where I learned about it. So thanks, Dave, for teaching me about this. It ended up coming in handy. But I totally would not use this if you were looking for speed. I think even in the best case, it's kind of slow, and I enjoy how ludicrously underclocked this particular one is. So I think we can look at the parameters with the ETH tool. ETH1. Yeah, so I guess it's also working in half duplex mode, which seems fine. Full duplex would work since this is... Oh, and I don't know which side is doing this, but one of the sides is automatically detecting which pair is transmit, which pair is receive, which is interesting. I think it's probably the TI chip. I don't think the ENC28J60 is smart enough for that. And I think this is also maybe why some of you might have seen this picture I posted on Twitter of a repair I did with foil. Let me see if I can get it on the microscope. Oh, just barely. Yeah, this was part of a failed earlier experiment. You can see so that black box that's mostly off screen is the transformer for the Ethernet, and I was attempting to, and I think this was when I was still trying to do most of the power monitoring on 3.3 instead of 1.2 for some reason, or maybe I was just trying to look at. No, maybe this was even after I was dealing with only the energy leaking into 1.2, but I was trying to kind of have less of a kind of electrical maelstrom whenever this thing is transmitting, because all the current that it takes for this microcontroller to very rapidly magnetize and demagnetize the coils in this box, all of that is going to end up just coupling noise into definitely the 3.3 volt rail, but then also to some extent the 1.2. So I was trying to mitigate that by adding series resistors on the transmit, and so I did some really tricky soldering, which I guess I have some photos of somewhere, and got these two resistors that were a little bit too big, just like standing up on those traces, to put like 47 ohms or something in series, because I thought that would help. And I was afraid it would just like completely lose my connection. And my connection was fine, actually. I could still talk through those resistors, and I didn't fry the board, but it didn't actually help with my noise problem. And then much later, after I'd taken these out because I thought they were causing another problem and I wanted to rule them out, and so I took them out and replaced them with copper tape links. Then I find out that it had been doing that auto switching thing, and this one wasn't the transmit, this was the receive. So the resistors, like, they weren't really affecting the impedance of the receiver that much, but I didn't really get a chance to test whether that would have prevented it from transmitting. So smart chip, need to figure out how to disable as many of its features as possible. All right, so the FPGA is actually something I would totally recommend playing with if, even if you're new to FPGAs. There's this project called Ice Storm. Oh, that's going to be difficult to Google for. If you search for Ice Storm FPGA, you'll find this page. And there are a few related projects, but this will get you started. Basically, this is I think an amazing milestone. It's really the first viable open source FPGA toolchain. So, and if you haven't heard of FPGAs before, just really briefly, they're programmable hardware. So, a chip that has a sea of logic elements, so little lookup tables and wires and inputs and outputs that are just kind of ready for you to wire up in whatever way you want. And so this is a software tool chain that is based on really detailed reverse engineering of in the image, in that binary image you give the FPGA, what do all those bits mean, and how do they configure all the logic elements in the wires? So this was the work of a few people, but I think most notably Clifford Wolf. He was the one who did the reverse engineering and wrote the bitstream compiler and decompiler. And so the upshot of that is that it's by far, I think, the least annoying kind of entry-level FPGA toolchain to get involved with, because you don't need like a 3 GB download. You don't need to worry about license keys and installing Windows or maintaining something that expects like ancient Linux binaries. Like, this is something you can compile yourself, and if it doesn't work, you can hack it until it works or submit a patch or whatever. And it's especially nice because the FPGAs that it works with are pretty cheap, and you don't even have to build your own board, because you can get like a dev board from the silicon vendor, this thing called the iStick, which I should just point the camera at since it's in a vise and I don't have one handy, but, oh, or actually since I have the computer here. Yeah, this is the thing. Do we have a picture? Yeah, this thing. So it looks like kind of a giant USB thumb drive, but it's, if you see that pricing, it is like under $30 including shipping. So I think it costs like $5 to get these shipped, but still, that is one of the cheapest FPGA development boards I've seen. And so something like this, plus these open source tools, actually make it pretty easy to get started with creating customizable hardware, which is really the only way that you can do this kind of thing, like taking a clock signal in at such a high frequency and turning it into something totally different and then outputting it again. Like, you could buy a dedicated chip that's designed to do that. Like, there's one from SI Labs, and in fact Adafruit has a breakout board for one version of that chip, but not the version of it that has like a clock input, which is what you need for this. So this was kind of a good solution in general, but also a good solution just for me given the parts that I had handy. All right, so it turns out this is actually all you need. Let me make clean and you can see how minuscule this really is. So 3 files for our hardware projects: a run-of-the-mill Unix makefile. This .v is the source code written in Verilog, and this .pcf file, which is named after the board that we're using, is actually just a really partial list of mappings between names in the source file and pin numbers on the chip. So that just tells us like how to plug this into the hardware. And we can take a look at each of these in a text editor. So these FPGAs that have been reverse engineered are pretty nice, and they're of course lower density and they don't have the features that you would find in, like a Xilinx or an Altera or something, Xilinx or Altera. But that's part of the reason they got reverse engineered, is because Clifford wanted to pick something that didn't have tons and tons of features, but was also also had reasons that you'd want to use it. So it is inexpensive and it's low power. So those are both pretty good pluses. And the toolchain also supports the larger variant of this. This is the HX1K or something like that, and there's also an HX8K. So this is all the source code we're dealing with, and a lot of this is just kind of not even especially necessary for the job. So I think I kind of want to talk about the tool chain first, though, just to get that out of the way before diving too much into the source. So you can actually get a pretty quick feel for the tool chain just by looking at the makefile rules. So we're starting with these Verilog files, and this .blif, I forget what that stands for. But it's a type of netlist format, so it's a representation of a bunch of electrical gates and how to connect them together. And that includes like abstract gates, like, just ideal, NOT and XOR, that kind of thing. But it also includes, oh, actually, let me try, I think the stream is lagging a little bit. Let me try turning down the resolution of this computer very slightly. Oh no, I think I hit that, mouse bug that I was having trouble with. I have a plan to replace this, this air server based thing. I'm going to try to see if I can get another HDMI input on the streaming machine with USB 3. Oh, come on. Oh, there we go. Okay. Did not remember to turn off Synergy before starting this adventure. Okay, a little fewer pixels, but I'll zoom in to try and compensate. Oh, a little bit too big still. I'm like making the window smaller until I see OBS hit 30 frames per second. So it's somewhere along the line it's scaling it down just so that it can scale it back up again later. I think that's it. I think that's gonna be close to 30. All right, pardon the technical glitch. All right, so yeah, the make files for this toolchain are nice and clean too, especially like if you've ever tried to compile like with a Xilinx board and make files, especially if you've ever tried that running the tools in Wine, it gets pretty hairy. But the steps are actually pretty similar to if you've seen other FPGA toolchains. So there's one step that takes the really high-level description in Verilog and converts it to a logic description in this BLIF netlist file. And so that's just like, converts the kind of higher level like register transfer description that's in your Verilog code to just a sea of gates and how they're connected. Then the next step is this program Arachne place and route. Oh, I'm getting slightly ahead. So you do kind of have to know if you're using this toolchain that there are a few separate components and they're in separate repositories that you have to like compile and install separately. It isn't like a single bundle yet. And that's partly because of kind of applicability, because these are each useful for different sets of like, for example, these tools that start with ICE are part of the ice storm repository, which is this kind of reverse engineering effort. And so the ice storm tools are only relevant to this particular like ICE40 series of FPGAs by Lattice. But a lot of these tools are made to be general so that once other FPGA series get reverse engineered, then with the addition of some new data files and some new features, the other tools could be made to work with those FPGAs, whereas like the packing tools and the timing analysis and the actual USB programming tool, like that's all going to be really vendor specific. So that's what these last steps are, just converting the ASCII description of the cells on the FPGA into the binary file that gets sent to the device, going back and figuring out how long all the delays are going to be in the finished design to make sure that it hits the timing requirements, and then actually copying the design to the board. Those are all the board-specific features that kind of ice storm itself handles. But then these other two big steps, the synthesis step where we're going from Verilog code to the gates, that's handled by this tool called Yosis, which is another whole big, like that's actually like by weight of code, by far the biggest thing here, because it's like a language compiler, you know, like any other language compiler, but it's for hardware instead of software. And so you can see here that it's this whole general purpose tool, but in this case there's actually like a script that's built in or that comes with it that does the synthesis like using the library of primitives that this FPGA expects. So it's kind of general purpose, but it also has to know like what it's mapping your Verilog code onto and like what it supports, and like it has to have libraries of primitives that it can take advantage of. And then this place and route tool called Arachne PNR is also designed to be pretty general. And it's taking all of those gates and trying to fit them into the physical resources available. So the matrix of logic elements, it has to figure out where things go and then how to use the interconnect to actually wire up the inputs and outputs. And so there's a lot of abstraction here, but the end result is really just ones and zeros, and so those get stored in memory. In this case, I don't actually have memory attached to this FPGA board, so I'm just sending it every time I start up the FPGA. So you could do that with another processor. You'd get this binary file from this toolchain, and then on a Raspberry Pi or an Arduino or anything else that can get the data there, you just send it basically like writing to an SPI peripheral, and that loads the ones and zeros into SRAM in the FPGA. And then those SRAM cells provide configuration data for all the internal routing and the lookup tables and all the other bits that the FPGA is actually made of. So what are we telling this to do? Well, just to kind of save the big one for last and get the IOs set, we don't have a lot of inputs and outputs here. This FPGA has a lot of pins that we could be using, but other than some LEDs, which are really just for debugging and for show, we just have the clock signals we're dealing with. In this case, we have an input clock from the chip whisperer, and then 2 output clocks going to the Ethernet and the microcontroller. So the Ethernet here is the ENC28J60 adapter. And these I've just picked to be mechanically convenient. This PCF file is a pin constraint file, and normally you just use that to set the name of a signal and then what pin it goes to. But this is also where you would set like timing constraints. So if you want to make sure this is, so if I was going to tell the software like give me an error if this clock couldn't actually be safely driven to 30 megahertz, then that's the file I would put it in, and it would run those constraints for me. So now that I know kind of what the environment is, so we're compiling this thing with the synthesis library for the ICE40. We know, we know where all of these inputs and outputs are connecting using the pin constraints. Then this is really the main function, basically, this top module for the Verilog code. And unlike software where we have a sequence of instructions, this isn't a sequence. It's just like a collection of things that all exist at the same time. So one of the things that exists on the FPGA is a phase-locked loop, which is basically a clock multiplier. It works by using an actual analog thing, so an oscillator that runs at a higher frequency that you can control. And then it controls that oscillator, kind of nudging it up and down to synchronize it with the clock that you're giving it using a feedback loop. So itself, it's kind of this little servo loop that's homing in on the right frequency. And these are parameters that mostly come from a little tool that comes with IceStorm that generates like divisors if you give it the frequencies you want. So I was like, I've got 30 megahertz coming in, 150 megahertz coming out, and it tells me what numbers to use for these parameters, which I think just add up to multiply it to, I think it's actually slightly more complicated than just a straight multiply by 5. It actually multiplies it up to a pretty high frequency, like 600 megahertz, and then divides it again because that's just, most PLLs are designed to have a stable internal oscillator that runs at a pretty high frequency like that. I don't actually know the analog reasons why that's more stable to operate at that high and then divide, but probably has to do with the magnitudes of the component values that you actually end up using in the circuit and the physical space available. So these things up here in the kind of pound sign bracket, these are parameters for a block that we're instantiating. So just like this top module is, like a function in a computer language, a module is just kind of a unit of reusability. So because of the way that we're compiling this and like giving this as our kind of top level source file, this acts like main. But this thing down here is like the same kind of an object. So like we're creating a function here, basically, we're creating a module. And down here we're using an instance of a module that the library has defined. So the standard library for this chip basically knows how to instantiate one of these modules that links up to a physical thing that exists on these chips. So this is how we're effectively using a resource that exists physically. which is what we're always doing with an FPGA. You know, we're never like instantiating a brand new thing. We're always just connecting things that exist. But some things are special, and there might be an especially limited number of them. So like clock multipliers or memory blocks. Sometimes there are special hardware units that just do like binary multiplication, or there are hardware units that are an entire CPU. So we're setting this thing up to act as a ×5 multiplier that is suited for this particular frequency range. So it's good for 30 megahertz in and 150 megahertz out. And we're wiring it up using these, which kind of act like the parameters we're passing to a function in a programming language. These are sort of like what wires we're attaching to the module. And it's kind of like, you know, it's kind of like these parameters up here. The data types here could be single wires that could be inputs or outputs or bidirectional. They could be like arrays of wires that can be treated like numbers. And so here we're wiring up some of the signals. We're saying that the reference clock we're using as input, the thing that we're multiplying, is the clock that we're getting from Chip Whisperer. So we're just wiring that directly to the input up here. There's nothing in between there. It's just interconnect. And then the output is going to this internal signal called IF clock, which is just going to be like a temporary wire. And I'm actually noticing that normally I would write that with an explicit wire declaration. I guess it doesn't complain if I don't, but it's probably good practice to declare that wire. And so that's just saying like this is a single bit electrical signal. And you know, you could use that for data purposes, or you could use that as actually a clock that drives other logic. So in this case, we're actually using this signal as the edge that causes other logic to make progress. So in this case, that intermediate frequency clock, which is our 150 megahertz, is actually driving this divider circuit. So every time that 150 megahertz clock experiences a positive edge, the logic inside this clause runs. And when I say run, it means that what's actually happening here electrically is this is building a circuit where this counter has a pathway routing a signal that's being computed as that counter -1. And it also has a path where it's being routed to this other value where we're taking a constant and setting it to the counter. And so what that actually does is it creates kind of a decision circuit where this counter always gets some input on every clock cycle, but depending on the value of this calculation, so whether or not the counter is 0, it will either assign it a value based on this path, or it'll assign it a value based on that path. But on every clock cycle, something's got to happen. You know, and if you don't assign a value specifically, then it's implied that it takes the old value. But for example, you couldn't assign both of these on the same clock cycle. That would just, I mean, that would either generate an error or just be kind of useless code, depending on how smart your synthesizer is. So in this case, this is kind of idiomatic. Like, we're writing this expression that you can read a little bit like a programming language, but with this knowledge that everything happens simultaneously. So we're saying that on each of these positive edges, so everything in here, this all happens 150 times, or 150 million times a second. All of this runs, you know, with no exceptions, always happens. And if the clock's previous value, so when we're referring to this, this is always the value it had on the last clock cycle. And when we're writing to it, it's always the value it has on the next clock cycle. So here we're just saying, you know, if this clock is about to overflow, then we're going to reinitialize it using this kind of pre-calculated divisor value. And at the same time, we're going to toggle this other value that's stored in a separate register. But if it's not about to underflow, then we can go ahead and subtract 1, and we don't do the toggle. And because we're not setting this value in this path, it's implied that it's the you know, unchanged, so it doesn't have that toggle. It's just the same as if we had said output clock, arrow, output clock. So as a result, this is a simple clock divider. It ends up counting down from this preset value, this divisor, until it hits 0, and then when it hits 0, it toggles this other value, output clock, and then it just keeps doing that. And so that runs simultaneously with this thing up here. So while this is getting the clock from the chip whisperer and multiplying it up from 50 to 150 megahertz. This thing down here is taking the 150 megahertz clock and dividing it down again by this weird number 24 to get the 6 1/4 megahertz clock that we want. And then just some more wiring again. We can just take that output clock and just connect it directly to both of those output pins. And so that'll cause interconnect to be generated, like buffers and wires, but no combinatorial logic. And then just, this totally is unnecessary, but I wanted a bit of an indicator that my clock is ticking away happily. So this is generating, I can actually get this on the camera in the corner. This is generating a little bit of LED bling. Which is conveniently under the Ethernet cable. Yeah, sure. So you can tell that that's clocked by this pin. If you just pull that out, you can watch it stop, and you can put the clock back in, and it keeps going. Not a lot of chips like having their clock stop like that, but sometimes this one's fine with that. Sometimes the PLL loses lock. Currently, the way I reset the PLL is to just reset the whole FPGA. Might be easier to focus if I made that bigger. Oh, I turned off Synergy, but I don't have keyboard focus in the thing that lets me change channels. Yeah, I do need to make maybe a dedicated button instead of this thing that relies on the keyboard focus. Something with a weird keyboard combination that I can have OBS trap directly. That would be nice. Oh, that's why I can't focus. It's a little too close. There we go. Yeah. It's not the prettiest light show, but it tells me the clock's ticking. So yeah, that's just 2 bits from a binary counter, and then those same 2 bits inverted on 4 LEDs. And then the middle LED is just wired up to the PLL lock signal. So let's go back to the computer. So this is going to look a lot like the other thing, except now we're using yet another clock. FPGAs are really optimized to not use a lot of different clocks because, even though you typically can use any signal as a clock, they usually have a special distribution network that can handle, taking maybe a couple of clocks or maybe 4 clocks and getting them all over the chip, just giving them a way to go to every single flip-flop, every logic element in the whole chip. But and so in a design like this, maybe the optimizer decides like, oh, this thing, you use it as a clock once. I'm going to assign it to a global clock buffer. But usually that's not what would happen, and this would just be this wouldn't necessarily be the most high performance way to use clocks. You would usually want to stick to, a smaller number of clocks and perhaps have, like a high-speed clock that does something really quickly and then stops, goes back to sleep. But in this case, we are just using this FPGA as kind of a PLL and a divider. So yeah, these assignments are nice too. These just create, so like whereas these always statements with the with the arrow here, these imply a flip-flop. So like a logic element that stores a value and then like holds on to it so that the next clock cycle can use it to compute another version of it and so on. These assignments don't include any storage. They're just wiring. But when you wire things together, you can also do calculations, and this is combinatorial logic. So in this case, it's simple, it's just an invert, so I'm just using the opposite value here. But you can actually do fairly complicated things without even having to store intermediate values. That just limits the maximum clock speed your design can run at, because the clock speed is often limited by what is the one most complicated thing that you have to do between clock ticks. Well, that's the shortest you can make those clock ticks. So that's a really good motivation to split things up into smaller stages, like pipelining. Oh, yeah, I'm just catching up on chat briefly, and the cat disappeared. He's upstairs. I can tell he's using the litter box because I can hear him. So maybe he'll be back down in a bit. All right, so let's install this. I can demo how easy this tool chain is. So I'm going to type make. Oh, do I not have that installed? Oh, maybe I didn't do make install on that. Oh yeah, maybe I'm not quite finished compiling it, so maybe maybe this needs a slight bit of compilation. If this ends up taking a while, we can do some soldering while it's compiling, but I think this is going to be fast. Oh man, that feels like it's starting at a pretty early stage in the install, so maybe I'm wrong. Let's make sure we had the other tools installed, and then maybe we can just move on to something else and not actually go through the compile right now. You know, I might have not had Yosis on this machine, just the programmer tool, and I might have compiled it on the other machine that I SCP'd this directory over from. So that might have been what happened, which is fine. It's still resident in RAM, and I think by the time we need to reload it in RAM, I'll have a new binary file. Yeah, so let's let that compile go while we take a look at the board. Oh, that's a good question in chat that maybe we can investigate without switching context too much. The question was whether we can see the logic elements that are used to implement the design after the FPGA software does its thing. And the answer is definitely yes. There are different tools for that depending on the platform. I know I've used something in the Xilinx tools before where you get this big graphical description that I don't know if it's like necessarily super practical, but you can really like zoom into each individual. So like from a really broad level, you see this big matrix of you know, usually like little elements that have like lookup tables and some flip-flops and stuff like that. And so you can then zoom into one of those and see how that element is configured. And then you can look at the space in between them and see the logic interconnects. And so there's definitely a graphical thing that Xilinx has for that. And I know, I mean, like reverse engineering, like they're definitely going to have tools for that, but I don't remember how those work. So maybe we can take a look at that. So it would be here in Ice Storm. The other thing is, I mean, some of that might even be legible in the ASCII file that we're going to get, because so this Ice Storm toolkit uses like an ASCII file as the intermediate format, and I think some of the bits might be labeled, but that's also still pretty low level. Icebox, yeah. Let's see if the website has anything, any clues. Yeah, so the ice pack thing, it does give us an ASCII file, but it's pretty low level. It's just ones and zeros for the configuration bits. And there's this higher level stuff. Here's a picture of the FPGA. Let me try decreasing this resolution even slightly more. It is, I was just noticing it's still lagging, and I don't want the audio to get out of sync if it isn't already. Go, Synergy. Alright. I think that new HDMI grabber that should let me avoid this low-res air server stuff is coming in a couple of days, so I think that might also relieve some of the CPU overload on the streaming machine, since it's probably going to be less CPU to shuttle some uncompressed data over USB 3 than it's going to be to do whatever crazy codec madness this is doing right now. All right. So it looks like in this architecture, and I mean, I've got some vague memories of going through the official documentation on this. And I mean, I think they even mentioned this in the iStorm project webpage, that if you really want to know what's in the FPGA, probably the first thing to start with is the official documentation, because they do actually talk quite a bit about the architecture, and I think that this tile layout is actually specified in the official like Lattice FPGA doc. But the main kind of secret here was like inside one of these. Well, now the reverse engineering effort has led to this amazing chart where you know, it looks like there's some unused bits, but then you also have details for which bits are being used for which parts of the logic operation, and this all kind of turns into a database that is both intended to be human readable for the reverse engineers at least, but also used by the automated tools like that Arachne place and route. Oh, look at all that compiling. Yeah, this definitely is bigger than the other things. Let me make sure that I actually have the place and route compiled too. Maybe I don't. Maybe I should start that one compiling too. I think I was having some kind of Yakshavy problem with libftdi on this machine, and that that distracted me from fixing the other tools once I got iceprog working. I was like, I have a bitstream file, I can program it now. Hey Tuco, are you down here and interested in Bolt? That's a big yes. All right. Where's the closest Bolt? There's one. Yeah, I really like this open toolchain, and you know, I'm sure that it's got some limitations still as compared to a full-size kind of full strength, full-size whatever SDK. But I mean, last time I was doing kind of some serious development with this SDK, there was no timing analysis tool, for example. You just had to kind of hope your design would run fast enough. Because that's like, FPGAs, if you're not familiar, have a totally different failure mode than a CPU when things aren't fast enough. It's like a CPU, sorry, this clip came off and I was just trying to remember where it goes back. I don't want to forget. That's better. Hey, Tuco. So like if your code doesn't run fast enough on a CPU, then it'll run slower, which is what you expect when your code doesn't run very fast. But if your code doesn't run fast enough on an FPGA, then it's like the data doesn't get there by the time the next clock cycle happens, and that clock cycle is still happening, so your data is just going to be corrupted. And so that's a big part of your job in designing hardware, is to make sure that that never happens, or at least as close to never as you can do within the limits of physics, which is pretty close. Okay, yeah, the place and route tool does not take as long to compile. Hey Tuco, I just wanted the compile to be on screen while we fetch. I was pretty happy that the this FPGA and toolchain and everything else was fast enough to handle that little 150 megahertz intermediate clock. I mean, there would have been other options, like I could have probably had the PLL give me, like divide that another couple of times, but it's always nice when you can have a little simple piece of logic like that run at a really high frequency without worrying. Oh yeah, just a clarification from the chat. This is the ICE40 open source toolkit that I've been using, and it's a bit of a rabbit hole for this particular stream. The kind of big picture here is more of a like a glitching setup, but I needed a way of doing some clock synthesis for the glitching, and of course FPGAs are pretty great at that. So so the thing that I had handy was this iStick, which is a cheap dev board with the ICE40 FPGA, and then this open source ICO-TC toolchain, which is Yosis plus Arachne place and route plus the what is it called? ICO tools, or I think it's just IceStorm. Yeah. Anyway, it's the names are still kind of a mouthful. I think they're trying to kind of brand the overall toolchain as ICO-TC or ICO-TC. But then like each of the individual pieces are still projects. So it's like the kind of standard problem you have with like Linux and a lot of open source stuff where like identity and convenience are sometimes at odds. But it's good stuff. And I think most of it's GPL licensed. Or no, most of it's BSD actually. Arachne place and route I think is GPL. But then I think the other two pieces are BSD or something like that. A couple of us, I think, have asked whether the Arachne place and route developer would relicense with something that isn't GPL, so I don't know if that's going to happen, but some of us are asking. You know, not like I want, like, I don't know, like, I think most of the reason why, I don't know, I used to like the GPL, I guess, and I guess the reason I used to like the GPL is, I don't know. I don't know if I'd actually thought about it that much. Like, it seemed like kind of the default license for a lot of things. And I think, to some extent, I liked the idea of kind of contributing to this shared base of code that benefited open source, but didn't necessarily benefit anyone who didn't play by that particular open source rule set. I don't know, and I liked that for a while, but then I guess I just started to see more and more of the ways that the GPL got in the way and like just kind of scared off people from contributing or using the project, and I had a hard time seeing it being a super helpful thing, except for maybe Linux. Like maybe Linux is better because of the GPL. Maybe some other like very large projects that you don't want to just kind of get wholesale pilfered. But for a lot of projects, it just seems like it ends up being much more of an encumbrance than a kind of safety net for those projects. I guess I can understand like the GUI toolkit Qt. I don't know if they're still doing this, but for a while they were dual licensing, so you could get a proprietary for pay license, or you could use it in open source projects if your open source project was GPL'd. And you know, that's not probably something I would do with my software, and it would potentially turn me off from using someone else's software. But it totally makes sense to me that they would do that, and I guess, you know, a lot of people were totally fine with that. Yeah, I'm really interested in doing things with FPGA tools that the commercial tools don't make easy. And I was wanting this for a long time, and even very briefly started to think about doing reverse engineering on my own with some small Xilinx FPGAs. But yeah, it's, I think I wanted to do something with like partial reconfiguration and genetic algorithms that would have been really annoying on like a Xilinx platform. Some of you have probably heard of this pretty famous genetic algorithms experiment with some FPGAs that are pretty old at the time, but they were kind of evolving this to find a circuit that was a frequency detector. So you'd give it a square wave at one frequency and it would say yay and it would say nay for other frequencies. And the kind of famously surprising result is that their algorithm ended up creating some circuits that satisfied the criteria, but only because of kind of electrically unintended consequences in the FPGA, so stuff that didn't appear to be connected but was causing like parasitic effects or and there are so many ways that could happen, you know, via capacitive coupling or coupling through the power supplies. So that's pretty interesting. And that definitely sparked my interest in, you know, maybe not achieving those same results, but at least trying to do some research on algorithmically generated circuits. And part of the problem is, you know, if you want to generate the circuit at like a Verilog level or something, then you're spending lots of time running the synthesis tools. Whereas if you want to generate the circuit at the bitstream level and just kind of permute the connections between components, that's what they were doing in this old study, but that only worked because the FPGA involved was so old, and because of its very particular architecture, it wasn't actually possible to damage it by just randomly connecting things. Whereas in any modern FPGA, that's not true. Like, it's easy to damage them, and the bitstream is, you know, much harder to modify in a useful way. So yeah, I think it would be interesting. And I'm already noticing some stuff where, yeah, that like maybe there are some open source uses for an FPGA that is configurable from, you know, like an ARM platform without a lot of memory and like partially reconfigurable at runtime with, you know, different bits that might be connected differently. Little flesh-eating tiger. When he's happy, he kind of likes gnawing on my hand, and I don't mind it. Oh, do we need mercurial for something? All right. Oh, there's another good question in the chat. Have I tried PSOCs, which are these, I think Cypress makes them. They're little reconfigurable doodads that are kind of like FPGAs or CPLDs in spirit, but they also, I think, have some analog reconfigurable units too, and yeah, they seem pretty interesting. I haven't actually tried them. Yeah, I'm kind of curious whether they might be a good, just kind of general purpose, like, shop Swiss Army knife for stuff like this, like what I'm using this FPGA for right now. Yeah, if so, I might want to pick up some and play around with them. Hey Tuco, this looks like a hard one. Can we install now? I don't know what ABC is, but I guess we need it. This is like late enough in the process. I wonder if this is a documentation thing. Huh. I don't know what it's compiling. Do we have a Yosis binary yet? We do. I think it's compiling like documentation or something. Yeah, it's just not installed yet. Maybe this is a testing framework? This looks like a logic simulator or something, maybe. It's something that knows how to read BLIF files. Tuco, are you still working on that same bolt? Yeah, you're still working on it? Do you want a hand? Where do you think it went? Oh, is this it? Is this it? Is that what you wanted, little tiger? Oh, nice. I should get this on the camera really briefly. The scope found some stable way of triggering, I think by locking onto some harmonic. I think we want to be servo AF again. Yeah. Usually not a huge problem. When I'm doing these like zoom shots, I have to worry about how much this sags after I lock the arm. And a little bit of wobble. It is not the prettiest clock, but it should do. Hey, Tuco. If this thing is serious about being 5% through compiling whatever ABC is, it's a fairly large package. Oh, thank you. Rescue from the chat from Sodium. ABC, a system for sequential logic synthesis and formal verification. So that seems useful. That seems like the kind of thing that is probably used to run the test suite. And I wonder if I can like install this without running the test suite, or possibly just temporarily put this in my path or something. Yeah, let's see if we can just temporarily work around this without it being a problem. So I'm just going to do that. It's just like installing it. So there it is. So there's our clock generator project. Oh. The text that's important really likes hanging out at the bottom of the screen, right where it's kind of crowded. All right. All right, I guess it needs more things. Yosa's binary is not enough. Well, maybe I wonder if the other stuff is still in the right like the right directory structure otherwise. Probably not so much. Fine. That was a great experiment. Maybe I should be throwing the bolt for Tuco instead. Okay, wait, whoa. Apparently that is a button that plays music. Okay, let me just, instead of demoing this right now then, I'll just copy the hex file over and we can move on to something else, because this seems like it might take a while to compile. I think this file was on my work laptop. Tuco, you really want a bolt, don't you? Okay, actually, yet a better plan. Instead of even worrying about reflashing the FPGA, let's just let this keep compiling, and I want to try pulling off that Ethernet transformer, because I think that's causing some packet loss, and it might be safe to remove both Ethernet transformers, but it should at least be safe to remove one of them. And so actually the one in this ENC28J60 breakout is like a mag jack, so the jack itself has built-in magnetics. So that might be annoying unless I have another jack with this similar footprint. Don't know if I broke that or not. My clock is still running. It also doesn't matter because I'm about to turn this off, I think. I just wanted to have a reference point. Oh, I can still ping it. Wonder why I can't. Wonder if this is a DNS problem. Yes, a DNS problem. All right, fine. I really like MDNS when it works, but it so often doesn't. So, yeah, I don't know. It's convenient for this network, but I might have some kind of, there might be some kind of dedicated DNS server in its future. So, like, this is okay, but I don't know, I mean, it seems like I'm getting, like, it seems slower than I would even expect it to be for this, so maybe I'm going to just do a ping flood and see if the waveforms look good or if I'm getting packet loss or something first. Well, the ping flood seems all right. Now, let's take a look at the waveforms. Well, maybe I do want to leave this on the scope. Yeah, I really do want to have both the scope and something else on the camera. One of my wish list items is like a better scope that I can also capture video from. That would be awesome. Like if the scope had any kind of video output, that'd be quite nice. Well, let's try something like this. Kinda. That's not the worst. Oh, Tuco. You still want stuff, huh? You want that bolt to happen. Where is it? I see one over there. Alright. So let's keep an eye on that 6.5 megahertz reference clock and start poking at the Ethernet transformer. Tuco, I hear you so much. Alright, triggered. Alright. So, next I want to know whether this is transmit or receive. I mean, it looks pretty clean. So I would guess maybe transmit, but... Oh no, maybe this is transmit. Yeah, I mean, this is a higher amplitude signal that seems like it's also running into some problems with, like, ringing in the transformer. But it's all nicely locked with the reference clock, which is nice. So... those were both on. All right, just to recap here. This is on the processor side of the transformer. This is transmit. Also transmit. And receive. And the other receive. And on the other side of the transformer, we have... oh yeah, there's the transmit after it's been through the transformer. Which actually looks fine. So maybe I don't need to worry about this. Like maybe, yeah. I thought that this was on the edge of what the transformer was handling, because if I underclock much more, that's when I start to see failures. And the waveforms were looking pretty grody, but that might have just been on, like I might have just been seeing all the kind of back EMF from the transmit, from the microcontroller side of the transmit transformer coil, and that's, for all I know, that's normal, and it's not going to affect the receiver side anyway. So yeah. That might be fine. So, okay, maybe move on to the next problem then, if that turns out to actually be not a problem. So the next problem was related to the glitches. So for that, let's switch to the actual glitch setup. No pings. The goal with this particular glitching setup is to try to find I mean, mostly it's to try to find parameters that are effective for this processor, but then like the next goal is to try to glitch this particular web server, like the one I'm getting this page from, in a way that causes it to return firmware memory instead of the web page, or in addition to the web page. So I've already modified this particular example with a little bit of code that just toggles a GPIO as a trigger every time this web server is about to look up a file in its flash, in its internal firmware kind of data structure file system thing. So let's put the scope back on that. That is this long wire between. This is going from one of the I/O pins on the TI Launchpad board with this the device under test, and that's just going right to the trigger input on the chip whisperer and nothing else except now the scope. So now I should be able to get the scope tuned by just reloading this page and getting the trigger. So that's channel 2. There it is. All right, so that, just for a sense of scale, since I know everything here is so small, this trigger pulse here is 500 nanoseconds. So that's about the fastest I get when I'm just, using the regular C API for this microcontroller toggling a GPIO on and off. So it probably boils down to a few instructions. But it's all underclocked, so. I think this will actually turn into a couple of HTTP requests. Yeah, you can see. So I think there might actually be multiple things going on here. So I do occasionally see this thing where within what seems like the span of one HTTP request, I get multiple triggers. So that might just be something else, some quirk of the code that I modified. So like maybe I modified it in a place that's slightly more general than I should have, since I think only one of these is real. But that only happens, I think, on some kinds of requests. Like, let's try something that isn't a whole web page, because this has multiple elements. Let's try just the image. This is a very low-res image, too. It's really weird seeing it progressively render a JPEG like that today. But every time I reload this, it looks like the scope triggers maybe twice, maybe just once. Let's see if we can tell. Yeah, it looks like just once. Cool. So yeah, that's how it's intended to be used. When you reload, when you load the whole web page, you're making a bunch of individual requests. And it also could be that maybe they're just bunched together because they all got received like during the same interrupt, and they're all just getting processed at the same time, but then the answers will go out asynchronously. That's not what we want so much, since it's much easier to test things one at a time. So what we really want is just a single HTTP request. So we have an answer for that. So this is the Chip Whisperer software. And to make things easier, there's like a virtual machine you can download from the Chip Whisperer site that includes all the prereqs already installed. But if you go through slightly more, kind of gathering of software, you can get it installed on your favorite Linux or Mac OS, or probably Windows. I don't know for sure. And so a lot of this, is covered in the official docs, and I've covered some of this before in my videos. Some of the new stuff here, this doesn't know anything about the FPGA stuff that's going on, since as far as this is concerned, the clock it's generating is the same as the clock that the microcontroller is using internally. And the clock synthesis we're doing on this FPGA is really just intended to counteract the, to be the inverse of the synthesis that's going on inside the microcontroller, but to also still give us the clocks we need for Ethernet. So this is going to assume the 30 megahertz processor clock, and we're going to try to have a 120 megahertz A to D here to sample it. And let's see, what else? So the module here is interesting, the target module. So in the past, so the chip whisperer examples mostly use this simple serial module. So it'll trigger the operation. Oh, Tuco, you want to play? So the idea behind this simple serial protocol is like it's easy, if you're trying to test a crypto algorithm, which is a lot of what the examples in Chip Whisperer are geared for, then you can take your algorithm and deploy it onto whatever microcontroller is handy and have it read from a serial port. So there's a good basic module in. Oh, Chico, that landed on the chair. It was soft, so you couldn't hear it. See it? Oh, he's got it. So Chip Whisperer has these target modules that act as just an interface between this kind of general Python like IDE, not the thing with the code in it, but the thing with the traces in it. This is like an IDE for doing like side channel analysis and glitching. And so in this case, can I just run this? Is this still set up to go? It is. Great. So when I click this, I'm running a capture and a glitch. If I zoom out, so that mess here is my attempt at a glitch. It's not really doing anything right now. It doesn't seem to be affecting the processor, but that's what I've got so far. Just to try to get it to do something, I have a bunch of repeated glitches, and I've been tuning them. And with earlier iterations of this, before I did the underclocking, I found some glitches that would at least crash it, but I don't think they were really synchronized very well with the target's clock. So this is kind of starting again with finding tuning parameters, but with this new clocking setup. So then over here, this is actually more of the signal we're looking for. I think there's actually still a good amount of different sources of a signal here. So I think that some of the medium frequencies here, like what we're seeing, like this overall wiggle here, I think that's actually noise and not coming from the CPU's execution, or at least not very much. But then if you look closer, this kind of higher frequency stuff, I think is actually mostly coming from the CPU because, well, actually, let me turn off the glitch, and we should be able to see that staying fairly stable, which is what I was looking at earlier. So I'm going to disarm the glitch. I also occasionally see this where there's just tons of noise. I think that might be when I'm doing two tests back to back too close and I capture during an Ethernet packet from the previous test. So I don't know about that theory, but so you can see when I run this, that overall wiggly pattern is not stable, so that's not related to this thing I'm triggering on. It could be, like the two biggest sources that I can think of for that are going to be noise coming in from, outside of this part of the system, so coming in through the 3.3 volt rail. I've got a filter on there right now that I actually just beefed up earlier today, but it doesn't seem to totally get rid of all this. But I think, well, so, but if you look at this pattern, like the lower frequency pattern, even though it's not particularly stable, does seem like it's affected by the control flow in this way that might be kind of data-like. So, I mean, I think it could be external noise or it could be the LDO. So this chip has an onboard regulator that I can't really disable or work around. And I think especially with the lower capacitance that I have it on right now, it might be just oscillating a bit. And so it could be that the higher frequency stuff is coming from the chip itself. So this is electrical noise caused by little differences in power consumption as it runs, depending on the data that's going across the bus. But then maybe the lower frequency components of this seem more like they're related to the LDO regulator. And so the little perturbations are kind of causing the LDO to try to correct, and it's not quite stable. So my solution so far has been to try changing the capacitance over the LDO and to see if this pattern changes. The last experiment I did along those lines was to just increase the capacitance from 1 microfarad to 2, and that didn't make a lot of difference. But I might try a more dramatic change just to see if that is at all related to this problem or this noise source. It's also not necessarily a deal breaker because I think I'm seeing enough of the stable signal now to have some more idea of what I'm doing with the glitches. So for example, let's take a look at the beginning of this and just run a few more of these traces. You see that? The signal is kind of moving like it's on the top of a, you know, it's like on a boat or something. But, and then there was occasional crazy things. But then that higher frequency pattern is just staying there. So like that's the pattern that is the result of this particular code path. So at the risk of this looking really messy because of those giant outliers, let me just try catching a bunch of traces. Oops. Let me have it overlay these. So yeah, so it's a little messy. You can tell it's a little messy, but you can also tell there is a signal there, and it's a real signal. So, or at least it's something that's very well correlated with this particular, you know, this particular trigger, which only happens once per test. So, I mean, it could be a really fancy clock harmonic, but it's probably code execution. So the other improvement I was talking about as far as helping the setup get a little farther along, yeah, I don't know if we'll end up even needing to take off the Ethernet transformer, but I definitely want to add a MOSFET, so the transistor that I'm using to switch this down to 0 volts briefly. I want to try sticking those like very physically close to the chip, so that I don't have to be discharging it over this long inductance and resistance that is this coax cable. Oh, hello to Aziz in the chat. Says they've been a big fan. It's nice to hear from people from all over and people who have been following my work for a while. Oh yeah, there's also something I almost missed about adding a video grabber to the Oscilloscope. And that's definitely been on my mind. In fact, like that was the first thing I thought of. It's like, oh, I want a video output. I'll just add a video grabber. And then it's like, oh, there's probably a solution that involves fewer distractions. Because I'd been thinking I kind of need a faster scope, so that'd been kind of like on my list of things to upgrade when the right need and budget comes along. And so I was looking just to see like what are the options. Like if I'm in the market for a nicer scope anyway, then what are my options for something that I can do video capture on? And that's even been pretty hit and miss. Like I can find some scopes that have like an add-on card that gives you a DVI port, which would be fine. And then there seem to be some scopes that have a VNC server, but not really like smooth frame rates. But yeah, just a little add-on that gives you a display mirroring port, you know, over USB 3 or HDMI or something like that. That'd be great. I'd like that. And especially if it would work on, you know, a range of scope models, like, you know, like I've only got this scope here. I mean, I've got like a CRT scope and a USB scope, but this is like my only like regular scope at this point. But maybe I can get enough information from teardowns and from friends to see if there are any like common like display connector layouts that I could, you know, populate a board for. Just have this thing with a bunch of different options you could choose between. That could be fun. Let's clear this mess, and let's get back to glitches, because so synchronization here is, you know, part of the reason it's so good is that we're like mega cheating and adding a trigger directly to the code that we're trying to glitch. But that's the stage we're at right now. Once we get it working with the cheating trigger, then we'll cheat less. And I mentioned this briefly earlier, but I have something that I think is almost as good as this trigger that we can use on kind of a real-world device. But this one is definitely, you know, I have a high degree of confidence that this trigger occurs before a particularly interesting piece of code. So let's zoom out a bit. And, you know, I think I was trying to show kind of what is noise and what isn't noise. And I can't really filter it out right now, but I think at least kind of trying to give you a visual impression of what that is. The other thing I was looking for is Ethernet traffic. I'm not seeing it right away, but maybe I have this timing set not like I expect it. Oh. I think last time I had this set up, the Ethernet was like just before the end of this trace, but maybe now it's just after. I'm going to try capturing slightly later. If we don't see the Ethernet, it's not a big deal. I also might have finally added enough capacitance that that doesn't start showing up in the 1.2 volts. What was that? Oh, is that it? Yeah, this is definitely less gainy than it used to be. This might be Ethernet, but it also might not be. I don't think this is it. It is useful to know when the response is being sent, because that kind of brackets the area we're looking in. And so I guess I haven't done that since changing all the timing with this underclocking and PLL setup, so maybe that's actually the next thing to do. Because we know that the beginning of this, so like 0 as far as where the chip whisperer is concerned, so when I set that to 0 and I run that, then this 0 on the horizontal axis is my trigger pulse that I explicitly added in software, that little like 500 nanosecond thing. Or microsecond? I think nanosecond. We're doing small things here, right? Yeah, microseconds are enormous. This is definitely 500 nanoseconds. Yeah, a millisecond is like, but I think actually a millisecond might be the time scale we're dealing with between like the response coming in and the reply going out. So we definitely want to get an idea of where the processing is happening before. And I mean, in this particular contrived example, because I put the trigger in, I have a pretty good idea that the interesting part is close to 0. But I still want to know when I'm actually sending the response. So let's kind of plot this trigger up against the Ethernet. Steal this probe. So I'm just going to tell this to just generate a bunch of traces. And so every time this runs, I also have it. Oh, actually, maybe that's a diversion I should get into before I get too far away from the computer screen here. So other aspects of this chip whisperer setup. So when I'm running this, typically the experiment has a couple of stages. You'll kind of send the data that you're interested in to the device and kind of arm whatever things are listening for the trigger. And then you'll tell the device like whatever it needs to do to start the event that you're trying to monitor or intercept or glitch or whatever. And then somewhere in that event, you'll find a timing reference. And either that'll be, you know, like something you counted from a reference much earlier, or it'll be like a GPIO. In this case, it's a GPIO. And then after that, when that trigger happens, that can then start clocks that you can use to then trigger the A to D capture or the glitches at a particular clock cycle post that trigger. So a lot of that is just you know, kind of built into the or to the FPGA and kind of infrastructure in ChipWhisperer, and we don't need to change it. But that kind of setup process needs to be different here. So that's handled by this target-specific Python module in ChipWhisperer. And in a lot of the examples, it's this simple serial thing that does all of its commands and setup over just a plain serial port. But this is a little module I wrote for this experiment called Simple HTTP that really just does the same thing, but instead of a serial string, you give it a URL. And so it'll do an HTTP GET from that URL, and the result that it logs is, which you can see down here, it's the HTTP response code, the length of the response, the SHA, I think it's a SHA-1 sum of the response, and then the HTTP headers. And so ChipWhisperer actually made that pretty easy to put together. I think it's just like a page of Python. Let me bring that up really quick. Software capture. Yeah. So you pretty much just have to dump a Python file in this directory and it'll show up in the UI. It's pretty nice. Oops. And so it gives you this whole system for creating like GUI parameters that you can adjust at runtime. So like over here, I've only used one of those. I've just got a URL string that you can edit. And then all of the parameters that show up over here, like they're backed by Python modules internally, but then you can also like script these really easily. So like I've got like an overall Python script that just sets up this particular experiment and tells me like, you know, what the clock settings should be and like what other modules to load. And so it can just kind of fill in all of these settings easily, including stuff like what URL I'm talking to. In this case, this is the IP address of the Raspberry Pi, which is running a proxy that proxies this request over the really slow Ethernet to the actual device. And so yeah, all of that stuff, like the Raspberry Pi being there, like I don't care at all about the timing of the Raspberry Pi itself or the SPI bus between it and the ENC28G60, as long as it's slow enough for the underclocked Ethernet chip to handle. And I don't care about the delay that the proxy causes, because the actual trigger I'm dealing with happens after the request is already starting to be processed. Another trigger that you can use, like if you don't have a GPIO, I was experimenting with using this on the kind of real-world industrial device before I found a better solution, which is to use the Ethernet receive LED on the board. Because those are usually driven by hardware, and so as soon as it detects a header on the Ethernet packet, it'll just turn on that LED, which is maybe just unilaterally more useful than a trigger on the sending side, like something like the Face Whisperer did for USB. But it's still actually not that useful because usually that's asynchronous compared to the actual network stack, at least in the cases I've seen. So it's not as useful to actually be synchronous with the interface from what I've seen in Ethernet so far. So we've got this parameter, URL, a lot of some boilerplate stuff. And then this is pretty much all it's doing. And so this is when the kind of ChipWhisperer framework is asking for its output during a run. It's just running a bit of Python code to use URL lib to look up this URL, read the response, and then kind of put together the string with the results. And the little summary string is nice because this can show up in Chip Whisperer's Glitch Explorer, which gives you a little summary of here's all the input parameters I was using, here's the results, and it can categorize the results as kind of useful or not so useful. And so to get the entire response, so like when this succeeds, eventually I'm going to want the raw data, because eventually this thing is going to be dumping out its firmware, I hope, over Ethernet. So for that, I have a packet capture running on the Raspberry Pi, just using TCP flow to log everything to an SD card. And so it'll proxy stuff from this test harness running in Chip Whisperer to the device just for the purposes of initiating the test. But then the actual timing is being taken care of by a dedicated wire running from the target to the Chip Whisperer. And then the logging of the of the goodies once I get the firmware, that's being done by a dedicated like TCP flow capture on the Raspberry Pi. So then this is just being used for analysis purposes. This is helping us narrow down what parameters are interesting. And so those are the strings that we've been seeing, like down here when we run a trace, result comes up down here. And what I'm looking for is, if a glitch is interesting, it'll change the length of this reply, or it'll perturb the body of it somehow, so this hash will be different. Or I might see something different in the headers, or odds are it might just crash entirely. But this is a nice summary which condenses all the stuff that's likely to be of interest when I'm at the glitch stage before I've actually found something that might be a firmware image. And then the Chip Whisperer tool has this Glitch Explorer window, which is just a summary of all of that. So this is the last thing I did. It has a date. And then I'm getting a little ahead of myself here, but when we get into tuning glitch parameters, this will keep track of all the different parameters that we've been working on so that we can kind of keep a catalog of what parameters had what effect. I can already see some earlier tests that just failed down there, but I wasn't tweaking anything. And there's a little doodad down here that lets you choose parameters from the automation over here to automatically kind of tweak on each cycle. And then you can even write these little Python one-liners that tell you when the data is interesting. So in this case, we're looking for something that is longer than this 1807 bytes, which is the usual length. So right now, it's doing all this data collection. It's sending out the request, it's storing the response, it's also storing the data on the Raspberry Pi, and it's collecting this waveform. But no glitch. So really, the missing piece here is inserting glitches that will hopefully disrupt the operation of the HTTP stack enough that it will return some data that isn't necessarily what it wants, and maybe eventually a usefully large chunk of the firmware. All right. I think this is everything I wanted to talk about with the computer-y stuff open. I think the next step might actually be... Oh, actually, no. I was trying to rule out the things I want to do before powering this thing off and soldering a transistor to it, but I can show you the glitches that I'm getting so far, and they just aren't super effective. But right now they're off, which is why they aren't showing up at all. So if I triggered the glitches using the other trigger, so now I'm just glitching right at the beginning at 0. And I'm doing a bunch of glitches in a row. So these parameters control the clock glitching module, or the glitching module rather. You can actually choose to inject the glitches in a number of ways. It actually might have been convenient to inject the glitches into the clock signal instead of into the power, since we're already feeding the clock signal to the chip, and then we wouldn't be fighting against the voltage regulator. But unfortunately, with the phase-locked loop doing the clock synthesis in the processor, we can't really inject glitches. That'll just kind of eat any glitches we put in. So instead, we're glitching power. Although theoretically, if we had some other kind of glitch, like an electromagnetic pulse or a laser or something, we might be able to hook it up to this. And so these parameters control the shape of the glitches, And right now I'm just repeating this a bunch of times. If we put in just 1 here, then we should just see... You notice it's not just 1 pulse. There was 1 pulse going out, but there's this ringing that's left over from the combination of the inductance in the circuit and the load dropout regulator itself trying to kind of trying to settle back on the right voltage after being perturbed with this huge instantaneous current load. So the scale here is kind of arbitrary. You can see that the glitch is much bigger than this waveform that we were interested in that had something that looks like code execution. I think that maybe we're not actually creating a glitch that's all that big on the power rails though, so I want to see if we can just take a look at this using the standalone oscilloscope and try to correlate that with what's going on. Where did our cat go? Oh, he's over there. I guess he wanted some more space. All right. So let's go back to the DSLR. I don't. Oh, there's another question in chat about. Actually, there are a bunch of people talking about the kind of the oscilloscope display capture problem, and then there's a question about the resolution being fairly low, and whether like a 480p signal would actually be capturable with a lot of HDMI hardware. I have a couple of HDMI grabbers right here, and they are both very different. I've got the Blackmagic. It's the Ultra Studio Mini recorder. It goes to Thunderbolt without compression, which is nice. It's very picky about formats. Like it has a hard-coded list of kind of the standard video studio production kind of format, so like NTSC and like 1080p, 59.9, 60, 30, you know, interlaced progressive. So it's got those options, but you can't just like pick up any signal you want. And then I've also got this device that's made as like a video game console capture box from Elgato. And it actually seems to be really good at just handling whatever I throw at it. So I'm kind of curious if that would be able to handle something that's kind of clocked weirdly. But yeah, maybe the most reliable option to put something that's more of a generic data pipe, like a USB 3 FIFO or something on it. All right. Okay, I can kind of get this on screen. So when I click this, I'm triggering a new trace. I think I want. Man, this is really wide. I want to be probing something all the way over on the chip whisper. Okay, first step is the input signal for the glitching MOSFET. Ooh, it's so little. Yeah, so this is glitching it while it's still in the middle of that GPIO toggle operation, which is probably not super helpful. Oh, why is that so little? You know, this might not even be really charging the MOSFET capacitance plus now the scope probe capacitance. Just to make this a little more visible, I'll try 4 repeats. There we go. signal looks kind of weak. I mean, it's obviously still rising when it decides to start falling. You know, it might just be I haven't used this particular glitching setup at such a high clock speed yet, because I am running the Chip Whisperer's clock at 30 megahertz right now. And so let me just try cranking up the width of these pulses. Like, try doubling it. That's a little nicer. It's a little weird though. I have the repeat set at 4, and I'm getting 4 glitches plus like a little tiny like pre-glitch. Like, what is that? So what does it look like if I set this to 1? Alright, that's one glitch. I wonder if the little pre-glitch is just like changing the state of the I/O pin somehow before the glitch engine gets started. I don't know. That's like 5. Alright. Anyway, we have something we can see now. This is a glitch. And let's just make this relatively wide. Huh. Yeah. Apparently, if you set the glitch offset too small, the glitch does not end. Which might require a reboot. Okay. Let's try that again with less getting the MOSFET stuck on. I was adjusting the glitch offset, and I guess if that's set too small, there's a bug, because I think I've hit that before. I think I might need to reset this board. Like power cycle. I'm having trouble getting this thing to come back to life. Let me reset the Chip Whisperer software. And this, I really get frustrated at this sometimes, but it's actually not so bad. When you think you have something set up, and then just all of a sudden, oh, it's just not working at all, and you got to backtrace and figure out why. So in this case, I think the target processor is just not running. So what happened is I was trying different glitch parameters just to try to get these on the scope, and I turned the offset down to a value which I think triggered a bug in Chip Whisperer, which ended up turning on the MOSFET for some amount of time until I could get another parameter in here, which theoretically could have damaged something, but I think it's more likely that I just need to figure out which thing to reset. Oh, this is not blinking anymore. Usually the way I reset that is by reloading that file that we don't have a compiled copy of currently, but maybe the compiler is done compiling. Yes, let's go back to the computer and reload this FPGA, because that's what needs resetting right now. Maybe I can point the camera at that before switching. Yep, our clock is no good. Need to reset our clock. So. All right, so Yosis is compiled and installed even. Yay. Can we make? All right, that's it. So we made it, and so that generated all the little intermediate steps. So the now I can take a look at what's going on. This will answer some of these hypothetical questions. So we've got a bunch of these outputs. So I think the first thing here, we converted the clockgen.v into clockgen.blif, which is the kind of logic netlist format. So you could probably, there's probably some program out there that will turn this into a schematic, like a graphical schematic with nice wires and everything. But that's the information this contains. It has the same kind of hierarchy model that Verilog uses with, you've got like a block that we're calling top, and it's got these inputs and outputs. And then inside, it's just instantiating a bunch of other stuff. So we have these gates. Instead of AND gates and OR gates and things, we'll usually find these lookup tables with 4 inputs, which are the kind of basic building block this FPGA uses. So then it says here's where the inputs are connected, and this is like an encoded representation of the function. Or no, that's not what that is. Where is the function? Oh, this is the function. That let init prem is the actual function that goes into the lookup table, and then this mess is actually just a temporary variable name. So, like, that's probably just called ABC because maybe that was the program that generated it. And then this is probably just like a number that increments. So this is actually implementing a digital counter. We've got a bunch of these lookup tables, then there are some general purpose, the lookup tables are the general purpose logic, but then we can also see some special purpose logic, like this is just for a carry chain in an adder. And then these things are flip-flops. So each of these stores 1 bit. This is the basic element of the kind of memory that gets built into logic. It keeps track of a bit as it's flowing through a logic circuit. And these are the parameters for the PLL that just go into some very device-specific stuff to get encoded to the hardware's format. So that's all we got in the blif file. And then I think the next step is that gets placed and routed, and then that turns into this ASCII representation of the format that's actually in the FPGA. So a bunch of 1s and 0s in really apparently no particular order, even though there's some very complicated relationships that explain how these work together. And then there's the binary file, which probably isn't super interesting, but is basically just those 1s and 0s plus a header and a footer, I think. Mostly 0s, because this FPGA is mostly empty. And then the .rpt file is, I think, a timing report. Yeah. So this goes back and takes the design after we've already converted it into the closest representation we have to the hardware. Now it goes back and figures out how long will all the kind of longest operations in here take. So this is actually telling us, I think this one on top is the longest. So this path, it would take some work to figure out what it actually means by this, because it's talking about a bunch of names which were generated by the compiler from this top level thing. It's kind of the equivalent of like attaching a debugger to something and seeing, the name of some temporary variable that the compiler would have emitted into the assembly code. But then it tells you actually this path took 640 nanoseconds, and so that's limiting how fast this particular clock can tick. So That's basically it. And the nice thing about this is all open source and you can read it all. So, and the upshot if you're actually reading this file is this tells you how fast the slowest circuit is limiting you to. So once we've got that, we have this program iceprog that actually takes that binary file and copies it to the FPGA. And because this particular board I modified to load directly into SRAM, I have this parameter. Oh. There we go. And now you can see in the little picture-on-picture window that the LEDs are happily blinking away. This program's pretty fast. Like, that's just the time it takes to copy 32 kilobytes over SPI into SRAM and then reset this thing a couple times. So, dynamic logic, if you haven't played with it, I would recommend it. It's fun to get into, and the tools and the hardware are way less annoying than they used to be. Alright, so have we unbroken this, is the other question. Yes, great. And now we've got some glitches. Now that we're turning the transistor on long enough that it actually turns on. This would be better at generating small glitches if we use some kind of additional preamplifier probably, because the MOSFET has a pretty high capacitance on its own, and so having some kind of buffer near the chip whisperer that drives the glitch signal over a cable, and then maybe another buffer near the MOSFET that drives the MOSFET, that might actually be the best solution. But that's what we're getting right now. And so this is being measured on that 1.2 volt rail. And we can't really tell how big of a perturbation this is, but the scope can tell us. So let's go back to the scope. I do have that other scope, that bit scope that I can put directly on the computer, so it's much easier to capture, but that's way too slow for this kind of stuff. That scope is 40 megasamples. So, I need more megahertz. Okay. Okay. So the top trace is the signal the chip whisperer is generating to drive the gate of the MOSFET transistor. And then the bottom is the trigger that our hacked up example firmware is generating. So one thing you can notice is the capacitance of this MOSFET is a huge deal. Like, it's not really fully turning the MOSFET on or off during the course of these pulses. So its effectiveness is definitely going to be limited. So that by itself might be a good reason just to buffer the input. But let's also take a look at that against the output to see how effective it is. So for that, I'm just going to move trace 2 to the auxiliary trigger and then bring in another probe. All right. So I think we've got another probe on the table. Hey, Tuco. You know what these are? Yeah, I'm lucky he doesn't like to gnaw these things in half. All right. What was that? I guess that was some ground bounce when I plugged in the scope. So let's take a look at the 1.2 volt rail. want to DC couple this because I really do want to see the absolute voltage levels we're dealing with. Yeah, see that? That's not so great. So I think this is why my glitches are not working yet. I don't know how much of this is due to not turning the MOSFET on completely, and how much of this is the LDO regulator just being too beefy and burly for me to overpower it with this little MOSFET. But the top signal is the gate of the MOSFET, and the bottom signal is the 1.2 volt rail, so effectively the drain of the MOSFET, but with some non-ideal electrical stuff in between. And you can see that that initial waveform, we're getting pretty much nothing. And then there's a bit of a, like, I don't even know what's going on down there. Like, maybe we eventually get a bit of a spike through, but that lag is very strange. I wonder how much of that is the cable. Because, I mean, we're getting that huge phase shift. I mean, I'm saying huge, but let's measure this. We're on like 50 nanoseconds per division, so that's probably like 100 nanoseconds. So that might be reasonable for the cables we're dealing with. So the whole thing is shifted over a bit, and also, most of all, just not that impressive. Like, we really want these glitches to be going down to 0 volts and kind of bouncing around a bunch. But all right. So I think that's everything I can think of to go through before the next soldering operation with stuff turned off and slightly different setup. So I'm going to refill my tea and then take a moment to answer any questions you have on chat or any suggestions for stuff to do before that stage. But then I'm going to put a transistor on this. Not realize how late it had gotten. I guess another option would be to do the transistor thing tomorrow and actually sleep. Oh, that's a good, let's see. Oh. US Water Rockets comments that they noticed I'm using a stick vise for the ice stick. Yeah, it's actually I had that particular ice stick previously. It's actually got a bunch of like double-sided tape residue on the bottom because I had it stuck to some other prototype board and I ripped it off right before this experiment. I probably should have had another ice stick, but you know, who knew? I'm low on FPGA boards around here. I just ordered a couple more ice sticks. Oh, there's also a suggestion as far as scopes go for using the Salier logic analyzers with analog. I'll have to take a look at that too. I mean, yeah, capturing from a PC scope is certainly easier. And so I've got that bit scope, and it's mainly limited by the serial connection. But I've heard some good things about Picoscope. I think they're using USB 3. Hey, Tuco. You want to play Bolt, don't you? But I don't know, I'm still a little distrustful of the performance I would get from a scope like that, and if I can find like a pretty nice standalone scope with a, where's the bolt to go? If I can find a standalone scope with a nice fast video output, that would certainly be preferable. Tuco, are you sitting on it, or am I just blind? Tuco, this is hard. Why are you making me look for bolts? That's your job. Maybe I'll cheat and get a bolt out of the master box. Oh, there it is. He was sitting on it. I mean, not like directly on it, but it was in front of him in a place I couldn't see it. Oh, there's definitely, that is a great idea. From the chat, a chat-controlled robot for the cat. I've been thinking for a while about making an internet-controlled cat toy that he can play with. Especially if it could involve these bolts and somehow have a robot that can throw them and, most of the iterations of this idea have me periodically refilling the robot's batteries and bolts, and I don't really mind that. Oh, there's a comment that it's strange for the MOSFET to have spikes at the gate from Wildmania, and that maybe I have some inductance. I don't think that's an inductance issue. I think it's just capacitance. But let's go back and look at the MOSFET some more. So, yeah, so the top trace here is the gate, and the bottom trace is the V-core. And so this, so are you talking about this signal over here being inductive ringing? I guess that could be the case. I mean, it could also just be a reflection from, like, I'm looking at the spacing here, and if you imagine that the distance between this wave and this wave is, one propagation delay over the cable, then what if there's a reflection that comes back over here and then ends up on the MOSFET gate? So maybe that's what's going on. Because I mean, the way it's set up right now, there's, let me see if I can get that on the camera. That's probably going to be important. Something like that. Maybe I should put some gels in front of these lights, make them a little bit cooler. Anyway, so it's still pretty invisible, but the MOSFET, there are actually two MOSFETs on this board that I think right now are just configured to run in parallel. But they're right over here to the left of where the probe is plugged in, and then this SMA is just connected to the MOSFET drain, and then the load is over here. So I think maybe the first, like, I might just try to isolate this a little bit by just disconnecting that SMA and try to make sure that the little wiggly tail on the scope goes away. I hear you, Tuco. Okay, I'm don't know if it's a good idea to unplug that with the power on, because it would be really easy to short out vCore. So I'm going to unplug this board. I hear you, cat. All right. Let's get this back up. Okay, board is booted again. Okay, this supports my theory that that was a reflection, because now we've got just these nice clean spikes where it's trying to turn on the MOSFET and having to charge the capacitance. Yeah, I mean, if I don't want to remove the MOSFET from my chip whisperer, because I kind of like it there for other boards that are slower, like I might just, like, I mean, this signal might be salvageable if I throw it through a Schmitt trigger. So it may be that I just don't do any buffering on the chip whisperer side, and then run this just through like a little twisted pair cable or something, and then have a nice beefy buffer or a couple of buffers on the side closest to the target. I think that seems like the most reasonable approach here. So, yeah, I think I've got a plan. I think my plan involves probably wrapping up this stream because it's pretty late here. And then I think my next step for tomorrow is actually to make a little tiny board. Like maybe I'll just mill something. And I can probably stream that too, like just do a simple board in Eagle. Because I think I just need a little thing that has a spot for a MOSFET and a MOSFET driver that I can stick on this. And I could just wire all that up kind of flywire, but it's getting to the point with like 3 or 4 components where a circuit board is definitely warranted, so that'll be a pretty quick little fab tomorrow. And if that goes according to plan, I think I can just have something that I just stick very physically close to here that has a FET and, you know, some kind of buffer. I'll rummage around and see if I have anything that might be a better FET driver, but at the very least I have some like Schmitt inverters that I can run off of 3.3 volts that'll work fine. And I might even just parallel out a couple of those if that's my problem. So I think I like that plan. I think we can stop the recording for tonight. Oh, there's another question in chat about the mill, and yeah, definitely. So I don't know if I have a time in mind. I'll try to give people as much warning as I can based on how the setup is going in the morning. But yeah, I'll get things set up and then try to warn people and have a stream where I'm just doing, yeah, a small PCB design. Probably in Eagle, maybe in KiCad. I think it depends on my mood. For something simple like this, I might do either. And then, yeah, we can just mill it out and put something together. And maybe I can also use this as an excuse to get some footage for my PCB population video, because that's something that I still need to get a lot of bits and pieces for. Well, I've got a full cup of tea. I'd totally stream a game of fetch with Tuco until I'm out of tea if he's up for it. Hey, Tuco. Oh, there you are. Do you want to play? Let's make your screen bigger, Tuco. Oh, let's also have focus. Yeah, I know, Tuke. You want to play. Where's the bolt? Oh, you've got a whole box of them. You're greedy about it now. Ha, no, I gave you that box. Focus. Oh, I might be looking for alternative webcam options. TucoCam is nice when it focuses. There we go. No? I wonder if there's something about the light that causes it to not focus, like coming from the kitchen. Oh, okay. I think I misunderstood the earlier question about the inductive ringing. I think that was actually multiple pulses in a row. So the multiple pulses was intentional, but the shape of the pulses was a little suboptimal, partly because it's not really driving the capacitance in the MOSFET with enough current to charge it quickly, but also I think partly because of that reflection that seems to be happening. I wouldn't have noticed that reflection if it wasn't for the comment, so I could definitely appreciate the prod to take a closer look. Let's see, as far as time, I mean, I'd probably start streaming, I don't know, maybe 12 hours from now or so, whatever that is your time. Maybe a little earlier if I get stuff together sooner. Maybe 8 hours from now. I don't know, maybe I'm pushing it. No, I mean 10 hours. 'Cause I could probably start before noon, even if I'm up late. There just always seems to be something that that I need to set up beforehand that takes longer. But I'm sure if I set deadlines, you know, I'm definitely going to stream at this time. I'll be able to make it. So actually, I think I've got a meeting at. Yeah, like 10:30 I've got a meeting, so... Oh, Tuco. Can you see that? I can't zoom in here. He can go so far under there to get bolts from under the cabinets in the kitchen. But yeah, I'd say it's probably safe to expect a stream on the PCB stuff and MOSFET, like, assuming I don't get to it before that morning meeting, probably sometime around, like, you know, I guess it depends on whether I can do something before that meeting. I might try to do a stream before that too, but it is nice that apparently, you know, I think I can actually stream a lot more of this stuff than I thought. I had some impressions about what needed to be kept kind of secret for now that might have been a little bit more conservative than they needed to even. So some of the stuff that I thought I needed to keep under wraps for a little while is just totally like, we can just talk about it. So that was part of what this was about, and there's some other stuff that we can talk about after that too, like, you know, the device I'm actually trying to glitch is, you know, it's like pretty run-of-the-mill, but also kind of interesting in context. It's this like industrial controller that's kind of like an Arduino for factories. Oh, there's a chat comment from Sodium about that it might be possible to pull the screen over USB. And actually, I'm remembering, I think I've actually done that. Because I was experimenting with the firmware for, I did a little hack on it, just really briefly as just a tribute for a friend. And it was, I remember trying out some of the USB interfaces, and I think I even found a program that lets you get the screen, but like I remember it being more of like a screenshot utility, but I didn't actually check to see how fast it was. So if it's, you know, if it's like interactive frame rates, then it might at least be kind of a supplement to other forms of video recording, at least. Chico, you're sitting on the bolt, and it's all the way over there. Oh, there's a comment in chat from Ryan, who does a lot of ICS work. What is that? I don't actually recognize the acronym in this context. There's also a question if I've had problems with tinnitus or tinnitus from after using the ultrasonic transducers for a while. I don't know if I would know, because I kind of have problems with that anyway, but I do remember feeling kind of some like ear/head weirdness after being kind of in close proximity to some ultrasonic transducers while I was working on them for a while. So I wouldn't be surprised if it is something that can give you like tinnitus or headaches, because I started to feel a little bit of that, but that was only from being pretty close to them while I was working on them for a while. Exhaustive search for all possible focuses. I wonder if it has trouble with the smooth floor. Like if it just doesn't have enough detail for it to find a focal point. ICS in this case is industrial control systems. So yeah, PLCs, programmable logic controllers, which is the kind of thing that has this Ethernet chip in it, is part of the whole industrial control thing. I have spent a lot of time lately, like, looking through documentation and stuff related to industrial devices, and I mean, even before I got a job doing like security research, I found that stuff interesting. One of the most like WTF moments I had on that recently was I was trying to track down. I think this was one of those tangents I got on while I was. Oh, Tuco, why'd you put it way over there? Does that mean you're done? I think I got on some tangent, like looking for radio transmitters or something, or maybe I was just like browsing DigiKey, and I found these parts that are like buttons with a built-in radio transmitter. Oh, or maybe I found these because they, you know, they're based on energy harvesting, which is why a lot of people find them interesting. So they're like a button that you press, and the action of pressing it causes a little kind of spring action thing to snap that moves a magnet really quickly past a coil, creating enough of a pulse of energy that it can power a little microcontroller and a little radio transmitter. And so doing that, it's a little button that when you press it, it just sends a coded radio signal that some machinery, like at your factory, can interpret. But of course, it has no kind of security at all. Like, it's totally susceptible to replay attacks, and anybody who can capture the ID of this button can press the button. So yeah, I see stuff like that just browsing the internet, and I wonder, like, oh, who's using stuff like this now? Well, I still have tea, but I think Tuco's tired, so I think it is time to end this stream. But maybe I'll see some of you tomorrow. I'll try to stream probably, you know, around noon, maybe earlier. I might try to stream earlier, but I'll try to at least be streaming around noon in case people want to check in late. And yeah, I'll try to capture as much of the kind of circuit board prototyping process as I can, and make a little glitching adapter for this board. Tuco, you got one more fetch in you? You're hogging this whole box of bolts. See, this is how the behavior is reinforcing. Usually Tuco gets into an infinite loop, but then when he stops, I restart him. Oh, is that one too hard? Maybe he is done. He seems to especially not like it when the bolts fall into an area that has other bolts. Because then it's like, oh, what's the point? They're just bolts everywhere. All right, have a good night, everyone.